Alright, you guys, welcome to video E4.1-8, I believe, and we are getting into the lab with this one, alright? So you should have up here what's on the left-hand side of my screen, the packet that says objectives, and you can also have that yellow worksheet with it, worksheet number 1, which is two-sided. It says topographic profile and geologic cross-section. On the other side is the well site data. Okay, we will be constructing this guy. But first off, looking at our document here, it says the objectives. In this activity, you're going to be asked to assess and solve a groundwater contamination problem caused by an accidental spill of a pollutant in a simulated exercise based upon real-world conditions. You'll employ a variety of groundwater principles and geological skills to map the subsurface or below-ground geology and evaluate groundwater conditions, and test well water samples to help determine the extent and direction of plume movement in the groundwater system. Finally, you'll summarize the results and make suggested recommendations to remediate the spill. So first off, we have a problem here. So you're a working geologist for the Clear Hydro Environmental Geology Company, and you receive this urgent email from a county CO or conservation officer. So go ahead and read this sucker. It's going to give you some background information. I then want you to turn over and read the first two paragraphs here, the materials and the procedure for part 1. And you can stop when you get down to the bottom of this page. And then I, as a demo, will run really what they're telling us to do here in number 2. So take a moment, pause this video, and read through this stuff. I'm not kidding about this. You cannot miss this stuff. Remember, this is a graded assignment. All right, we've worked with groundwater concepts for a while now. This one's graded. This is a big one, okay? So pause it and go ahead and check that stuff out. All right, you guys. So you should have read up through the procedures for part 1. I want to go back real quick here and take a look at number 1. Okay, I'm going to kind of model what you should have done as you read through this. It says, from Mr. Waters' memo, you know that the surface of the ground at the spill site is composed of gravel. However, you'll need to gather more specific info about the regional geology and the composition and extent of all surface deposits. So in other words, what are the materials? Is it gravel, sand, granite, or whatever, at the surface in this immediate area? Fortunately, this area of the county was surveyed and mapped some years ago for a highway improvement project. You were able to obtain a resulting geological map from the state Geo Survey that identifies the surface deposits for this area. With this info in hand, you've prepared a basic geologic map of the spill area. See map 1. Hopefully you went and saw map 1. I think you had to flip a page ahead. And decided to review the general characteristics and properties for each formation as presented in the data table. So, map 1, and I know this sucker's sideways, but you should notice here's the spill site, and as you go down to the bottom of it, you'll see, hey, from this dotted line to this dashed line, it is gravel. To the east of that, or to the right, the surface is sandy clay. But if we go to the left, it's clay. Remember, clay is considered impermeable. And then finally back here where it's kind of dotted or speckled, that is granite. Okay? So we know what is at the surface here. We go granite, clay, our spill site's in the gravel, and then we get to the sandy clay. It also said you decided to review the general characteristics of those properties, of those materials, in this data table. So on the next page here, it says general geology and characteristics of geological formations in the spill area. So we have a thin soil, and then we have our sandy clay, gravel, clay, and granite. And this tells us a little bit about these materials. So right now, some of the words you're seeing here that you need to know about: porosity and permeability. They are different things. I know the words sound a lot alike, but you might need to go back to your notes to see what exactly those definitions are. So pause here if you need to. Then we get on to number 2 here. To verify the permeability of each outcrop material, you've collected a small sample for testing. I have filled these vials with these materials. I have here a beaker of water with a pipette, and I also have a timer. What we have is gravel. Okay, It's a light material. You can imagine what gravel is like. There's lots of pore spaces. Then have, these two look a lot alike, I have sandy clay and clay. Hopefully you can see that this guy is a little bit darker. Now they both have clay in the word, and we know clay to be impermeable, or relatively impermeable. But the sandy clay is sandier. It's more of a sandy type soil instead of the very thick silty clay. I then have a piece of granite. Okay, regular rock, piece of granite. And I have to test these suckers as it says. I'm going to put some water, and really I'm going to see how long does it take for the water that I put in to sink down to the bottom. That's what I'm going to time, and then we'll make some observations in the bottom of our data table here. Right? So it says data table sample, gravel, sandy clay, clay, and granite. Make sure you are writing it under the correct one. Observations. Note the elapsed time for water to soak into the sample from the top down to the bottom of this little vial. And then also, basically, a little bit about it. So we're kind of looking up here at table 1. Did it go right through? We might want to rank how fast the water went through each of these, or if it didn't go through at all. We're going to want to know that stuff, okay? So let me get I have my table up here. I'm going to add some water into each of these guys, and I'll show you what we're looking at. I'm actually going to put it on the clay first, whole pipette, then the sandy clay, now my gravel, and for example, here's the clay. It's starting to go in a little bit, but generally it's sitting at the top. I'm going to skip over to the gravel here. And it's going in pretty well. Almost done, almost done, almost down to the bottom. Here's my sandy clay. So I'm going to let the timer run here. I'm going to stop the video for a minute, let the timer run out. I'll record these times and I'll report back to you guys so that you can fill out your data table. Alright you guys, so I have stopped my timer, and the gravel was about through when we finished up on our last piece, and it was 12 seconds. Right, it might have even been a little bit faster than that, but it was 12 seconds was as quick as I could look at it and see that it went through. Actually, it went right through the middle to the bottom. So gravel took 12 seconds to get from top to bottom. The next one, sandy clay, I just measured at 13 minutes, so 13:46. 13 minutes, 46 seconds for our sandy clay right here. And here's what the vial looks like. You can still see on one side there, it didn't get all the way through. But as I rotate this guy to the back, this is the side where I first saw it come through, down to the bottom. Okay, so our sandy clay took 13 minutes and 46 seconds. Now, clay looks like this right now. And I'm at about 20 minutes. Okay, at best it's about halfway. Alright, halfway, about all the way around this. As I recall from years past, the clay was still not done even as the hour finished. So I would like for clay at time, put 60 minutes plus, right, or greater than 60 minutes. It will eventually get through. We can see that right now because it's already halfway. It will eventually go, but it's going to take a while. The last one was a granite. It's a rock, you guys. Our direction said put 10 drops on it. So I did. They're still on top. It's a rock. Rocks can be a little porous to a degree, but we can sit here probably forever and it's not going to come through this solid rock right here. So the answer for granite is never. Never. It is impermeable. right? I put the 10 drops on. It sat through the whole time. It's not going anywhere, right? So your data table, after we did that, maybe you could talk about how, the sandy clay, there's still some pieces where it's not fully saturated. You could compare these three, rate them at what is the most porous, what is least porous. But we need to have that data before we move on. So this portion of your data table should now be filled out. Okay? So some observations along with the times. After that, I need you to flip the page, and you should probably go ahead and be looking at map 1 again, and note where each of our sediments are on the surface. At our spill site, we had the gravel, and we've just proved that that is the most porous, unfortunately for us. To the left or west, we have clay, which is pretty impermeable, and then granite, which is impermeable. But to the east, we have this sandy clay here, you guys, and it took a while to get through, but it did go through that. Okay, but our focus, the spill was on the gravel. So at this point, it will infiltrate into the ground and move in a certain direction based on this water table, or the aquifer, I should say, based on the aquifer. Okay, so from here, you have a few questions to answer on page 16. Make sure you answer both parts of the questions. It starts out, there's 3 questions up top. Which material was the most permeable? Which was the least? Do your observations match the descriptions in table 1? The kicker here is you have to make sure you're answering all parts of the questions. So part 1 had 3 things. Question 1 had 3 things there. Which was most permeable, which was least, and do your observations match table 1? Okay, the description in table 1. Second question, which material would make the best aquifer? Why? Think about this, you guys. You got to pick a material and tell me why. An aquifer has to allow water to run through it. So which material is going to be our best? Next, what other factor might influence the permeability of the granite sample? Could water move through the granite? Okay, probably not my piece sitting here like this. But in what case could it move through granite? You've probably all driven through the mountains, maybe heading south, through the Smoky Mountains or something, and you see that our highways are kind of cut through the mountains. They cut out or blast out big pieces of the mountains. And sometimes you look at that rock as you're driving by, and you can see water running down it. It's a flat wall. Okay, we cut the road into it, but we can still see water coming through. That tells us that water can get through granite or solid rock. Well, I don't want to say solid rock. What has to be there for water to move through? Okay, so think about that.